In this experiment, we have used one solenoid connected to a galvanometer with bulb attached between the solenoid and the galvanometer. At the starting, the magnet is at the rest, so there is no deflection in the galvanometer. The needle of the galvanometer is at the center or zero position. When the magnet is moved toward the coil, the needle of the galvanometer deflects in one direction. When the magnet is held stationary at the position, the needle of the galvanometer returns to zero position. Now, when the magnet moves away from the coil, there is some deflection in the needle, but opposite direction. And again, when the magnet becomes stationary at the point respect to the coil, the needle of the galvanometer returns to zero position. If you flip the magnet to bring its south pole toward the coil, the current flow in the direction that produces a magnetic field whose south pole faces the magnet. And if you pull the magnet away, it reverses, so the north pole faces the magnet. The galvanometer also will deflection in opposite way toward the change of direction flux. How fast you move the magnet determines the rate of the change of the flux. So, the faster you move the magnet, the greater the needle deflection. Next, we have compared with the different number coil. When we bring the magnet to a coil with less number of turns, the length will dim compared to the higher number of turns. That we'll know by increasing the number of turns in coil. It is easily seen that if the number of turns in a coil is increased, the induced EMF also increase. From the experiment, we can conclude that whenever there is a relative motion between a conductor and a magnetic field, the flux linkage with a coil change, and this change in the flux induces a voltage across a coil.